an indicator of these clinically significant antibodies. Could be antibodies that aren't clinically significant, but the indicators in the test tube, what we look for is not a color, as in chemistry, but we look for either agglutination or homolysis, okay? So when you take your 10 by 75 test tubes out of your centrifuges, don't give them a real hard shake until you look at the supernatant. You should have a button at the bottom of the tube that look at the supernatant for homolysis before you shake the tubes, demonstrating and looking for agglutination, okay? Now, having said that, the formation of agglutination is in two phases. And I mentioned that sensitization must occur first, then we have the binding of red cells together forming a lattice network. That lattice network is then visible through agglutination process. And I mentioned that the antigen-antibody reaction per se, if it does occur, it follows the law of mass action. So when the antigen-antibody complex does formulate, it can fall apart because the reaction can't reverse itself. Now, do you guys have any questions about anything we talked about thus far? Okay. What we attempt to do at the bench is control these antigen-antibody reactions that may occur in the test tube if both parties are available, antigen plus antibody. Things we do, number one, to induce sensitization, which simply means the attachment of the antibody to the antigen on the red cell. Number one. So on the red blood cell, we have various antigens. To identify these, sometimes we then attach a reagent antibody in the form of an antibody. Or, just the reverse, we're looking to find in plasma an antibody. Okay? So we provide a reagent antigen. This process is sensitization. Just simply the attachment of antigen to antibody, sensitization. You can't see that, and I mentioned this. You cannot visualize sensitization in a test tube. Okay? You cannot see visually the interaction of an antigen with an antibody on the surface of the red cell. So we want to make the molecule bigger. We want to make this thing bigger, bigger, bigger. How do we do that? Then we force agglutination, or we force the lattice formation to take place. Okay, sensitized cells just collecting together and making a big molecule and then falling out in terms of or agglutination. That we can see. Okay. Now, controlling factors. And this goes to, do you already have unit 2? And I'm using both, I'm going to go back to the short book and unit 2. Okay. So, variables that we must control when we want to force just sensitization as step number 1. In our situations, we would like to control the pH. And pH for optimum reactivity, optimum immunohematologic testing is a pH between 6.5 and 7.5. Now, how do we control this pH? Well, when we wash our cells and we make those 2 to 5% cell suspensions, we use physiologic saline. That's the salt solution that's coursing through your veins. The concentration of our salt solution is 0.85% sodium chloride. 0.85% sodium chloride, i.e. physiologic saline. We buffer this reagent. We add a buffer to our 0.85 physiologic saline, such that then the pH of this medium will always be 6.5 to 7.5, all right? There are few exceptions to maintaining this relatively neutral pH, and I'll talk about antibodies that require a little bit of a more acid environment, and we do provide that when we manipulate the buffered saline such that we could drop the pH, but I'll talk about those specifically a little bit later. So pH contributes to and promotes sensitization. Number two, temperature will promote and enhance sensitization. Okay? And it depends on the antibody type, the immunoglobulin type. And I mentioned this before, the two antibody types that we're concerned about primarily are IgG and IgM. That's why I asked you, what are your discussion about immunoglobulin? Now, as far as we're concerned, IgM, supposed to describe these, by the way. What are the features, what are the characteristics of an IgM type immunoglobulin? IgMs are monomeric or not? They're monomeric, but there are how many? Five. It's a pentameric type of configuration, right? There are 5 monomeric units combined and attached by what structure? What holds this pentamer arrangement of monomeric units together such that we can classify it as an IgM?
Is it the J?
It's the J chains. Okay, did you talk about that? Okay, so the J chains kind of combined and pulled together 5 monomeric units to create this pentamer. And that alone is referred to as an IgM. What about the IgG? Is it like an IgM? Is it pentameric? No. It's a monomeric, meaning what? There are only 2 heavy and 2 light, right? So there's 2 heavy and 2 light chains, which make up the monomeric unit. Now, so antibodies that we deal with can either be IgM type or IgG type, rarely IgA, I'll just throw that out there. Okay, rarely IgAs. IgMs are classified as cold antibodies. We classify IgMs as cold. We classify IgG antibodies as warm. Why? IgMs as cold antibodies will present via sensitization and agglutination at temperatures less than body temperature. The body temperature is what, 37? Okay. So if my antibody happens to be an IgM configuration, I'm not going to pick them up at 37. Okay, I'm going to pick them up at colder temperatures below 37. They really aren't cold, it isn't like sub-zero, okay? They will fall out at colder temperatures like room temperature, refrigeration temperatures, okay? So any test we do at the bench that we do at room temperature, which is about what? By the way, in blood banking, we always take the ambient temperature as a quality control measure. What should a room, typically room temperature be? What's the active?
25.
About 25, 26, right? But that's really not 0. So as far as blood bakers are concerned, it's kind of a misleading statement. But to distinguish between the two, we call them cold. IgG clinically significant antibodies will fall out where? At what temperature?
Body.
37, body temperature, right. So that's why we refer to these as warm. You'll pick them up at 37 degrees, okay? So if we're interested in finding antibodies of IgM type, we're going to perform our serologic tests at room temperature or below. If we're interested in picking up warm IgG antibodies, then we're going to perform everything serologically at 37. That means we're going to be working in a dry lab, okay, at 37 degrees. That also is one variable we have to control that allows for sensitization. Now, I already mentioned immunoglobulin type as being IgG or IgM. The next factor I want to mention, and if you look at figure 3-10 on page 69, okay, we're also interested in something called ionic strength. Ionic strength will also influence whether we will see sensitization or not, or provide sensitization or not. So ionic strength goes to, and going to cover a few concepts here, just talking about ionic strength and its influence on sensitization. We use various things called, and this is again in the test tube, and we're going to use every one of these all the way in our laboratory exercises. We use things called potentiators that can influence ionic strength. If you look at table 3-9 on page 69. All right, I'm going to go through each one of these potentiators. You've got to know the characteristic behavior of each one of these potentiators because we're going to use each one of these potentiators. First of all, normal saline, which isn't on here, but I need to add that to this list. Normal physiologic saline, and what's the concentration? 0.85% sodium chloride. Again, it's the same salt solution in your veins and arteries. Now, it's sodium chloride. When we take red blood, red cells can and must survive, and can only survive in saline at 0.85. If we vary that concentration, we can affect the integrity of the red cells. That's what the osmotic fragility test does in hematology. You just dilute physiologic saline down to water, okay, and it has a detrimental effect on red cells. Why? If you look at the composition of red blood cells, talking about the membrane is loaded with sialic acids, okay? Lots and lots of sialic acid molecules extending from and part of the red blood cell membrane. Sialic acid, okay, dictates the charge on red blood cells. All red blood cells carry a net negative charge, okay? And that's apparent in this diagram. If you look at figure 3-10, bottom of page 69, it's showing you a red cell. It's showing you that the membrane has a net negative charge. Okay? I have that illustration not only, I have that illustration in the handout too, the unit as well. Okay? So the membranes carry a net negative charge. Now that's important in terms of normal red blood cell survival. If we take a little drop of blood, maybe we can do this, you take a drop of blood, take a drop of red blood cells and throw it in normal physiologic saline, and it's wet now, look at it underneath the microscope, you'll see the red cells they'll matriculate to each other, but eventually they'll stop, and then they'll misdirect. And it's that negative repulsion, negative, they're gonna repel each other. They will not combine, and that's a good thing, you don't want clots to occur in the bloodstream. So the negativity of the membrane allows the red cells to kind of come to and close to each other, but they'll never touch each other. They'll shear away from each other, they're repelling each other, okay? That's preventing, okay, sensitization from occurring. And there eventually too, it influences agglutination, all right? Looking at this diagram, once again, there's some things I'm going to call some dimensions I'm going to call your attention to. First of all, negative red blood cells repulse each other. When we drop a drop of blood in physiologic saline, what's the composition of saline? It's sodium and it's chloride. Any salt that's added to a support medium will dissociate. Salt will break down into sodium ions and chloride ions, and that happens in our bloodstream. And when the sodium and chloride ions are free, okay, we have positively charged sodium ions, we have negatively charged cations. Now, because the red blood cells are negative, okay, the sodium and the chloride ions kind of rearrange themselves around each red blood cell. And that arrangement is that the sodium ions will come closer to the red cells. Why? Because the red cells are negative, sodium is positive, so that the charges attract. Now what we have there is then that's referred to as the ionic cloud. So if you look at this diagram, you can see the positively charged sodium ions represented. And you can see that they're more concentrated towards and closer to the red cell. And the further the sodium ions are away from the red cell, okay, the fewer in number they are, okay? So we call this the ionic cloud. Okay? Or two, another name may be the zeta potential. So by introducing red cells into sodium chloride, physiologic sodium chloride, just they remain intact, but they develop this ionic cloud or this zeta potential around the cell itself. And the zeta potential represents, if you would, as I was trying to describe, the magnitude or the thickness of this ionic cloud from the red cell out, okay? Okay. So you with me so far? Now that's normal. That's normal. That's what's happening normally. To define specifically this zeta, what's called a zeta potential goes to electricity, okay? The zeta potential is this force, and we can't see it, at what's referred to as that boundary of shear where the red cells slip by each other. They come very close, but they never bind, and they spread, and they slip, and they bypass each other. That's referred to as the boundary of shear, okay? So the zeta potential dictated by sodium ions, is that force, the zeta potential, the electric potential, at the boundary of shear when the red blood cells slip by each other. Okay? Still with me? Kind of follow it? All right. So the potentiators we use as reagents in vivo kind of affect this presentation, either the negativity of the red cell, okay, the ionic cloud, or the zeta potential, so that we can bring the red blood cells closer together, the sensitized red blood cells closer together. They can agglutinate and fall out as a button in the bottom of your test tube. Now taking another look at this diagram. Typically and normally, the gap between these normal negatively charged red blood cells is 25 nanometers. And you can see that in the diagram. Typically and normally, that gap is about 25 nanometers. The problem is this. If we have a clinically significant antibody of IgG type, okay, the IgG molecule in and of itself is so small, that being the distance between the antibody binding sites, this distance on an IgG is only 14 millimeters, okay? So the gap between the cells is 25, okay? 25 nanometers. But the spread, just looking at an IgG, is only 14 nanometers. Then if I have sensitized cells with IgG only, am I going to be able to cause agglutination of sensitized cells? If sensitized cells are coated with IgG, and the spread of IgG is only 14 nanometers, if this is only 14 nanometers, and the distance between normally our red blood cells is 25 nanometers, am I going to see, I might have sensitization, but am I going to get agglutination? Agglutination is the bringing together of sensitized cells to make a big clump so it falls out as a button in the bottom of the tube. So if this spread between red blood cells is 25 nanometers, but the spread between the binding sites of an IgG immunoglobulin to only 14, can I span this distance? Can I bring red cells together? No. 14 nanometers is not 25 nanometers. So even though I have antibody attaching to red blood cells, as in the sensitization process, if the antibody is of IgG type, I will not be able to pull red blood cells together because Ig is only 14. I can't span this difference, okay, with IgG antibodies. That's a real problem for us in blood banking. Because IgG antibodies are the clinically significant warm reacting antibodies body temperature. Right? Now, having said that, let's look at IgM. IgM is big. IgM is a pentamer. IgM is made up of 5 monomeric units. And look at its size. It gives you the size in the book. 35 nanometers. So an IgM type of antibody, okay, with a spread of 35 nanometers, without further involvement, can agglutination take place between already sensitized cells? You sure? Remember, this span is only 25. If IgM is 35 nanometers, can it span that distance? Can it overcome the negativity of the red blood cells? Can it overcome the boundary of shear? Can it pull sensitized red blood cells in contact with each other if it's 35 nanometers? Sure. So with no enhancement, no manipulation by by us, an IgM antibody, even though it's cold-reacting, can span the difference between the naturally negative red blood cells. Ask me questions. If you look at the illustration, again, either in the unit that I gave you or on this particular page, you can see an IgM antibody represented. Okay, you can see how big it is. And because it's as big as it is, it can certainly pull sensitized red blood cells together, because the typically normal distance between red cells is only 25 nanometers, and IgM is 35 nanometers. It can certainly span that difference and pull together sensitized red blood cells. Those red blood cells with an IgM antibody attached to its surface. Okay? Not only is it big, but because it's a pentamer, it has 5 times the binding sites, okay, of IgG. It has 5 times the binding sites of IgG, all right? Okay, do you have that concept? Any questions? Now, before I go on and talk about potentiators, on page 68, at the bench, when we must identify a type of antibody, whether it's IgG or IgM, we're going to take a blood sample and we're going to put it through what we call various phases. Those phases are given to you in table 3.8. All right? We will do an immediate spin phase. We will carry that immediate spin phase over to a 37 phase. And then the 37 phase into what we refer to as the Hg. So, on our worksheets, you'll have your immediate spin phase, you'll have your 37, and then you'll have your Hg. Okay. If I have an IgM, let's do an IgG. If I have an IgM antibody, okay, because it's cold, because I can pick it up at room temperature, okay, I will see agglutination in the immediate spin phase. Okay, so again, we do an immediate spin. Okay, we carry that immediate spin over to a 37, and you take this to and view all phases, and then you carry the 37 over to use the same test tube. You don't have to make up 3 test tubes here. It's 1. We take the immediate spin. After we read the immediate spin, then we'll perform a 37 phase on that test tube. After we read that test tube at 37, we will then do an AHG phase. Now, if I have an IgM, because it's cold reacting, because it's big, and because it has 5 times the binding sites, it very easily can pull sensitized cells together. I don't really need to do any manipulation. I will probably pick up my immediate my IgM type antibodies in the immediate spin. Okay? If I have an IgG, that being small, okay, a monomeric unit, just a couple of binding sites, okay, cannot span that distance between the red cells, then I have to do some manipulation. Immediate spin, I probably will not pick up my IgGs. Okay. I may, and I'm gonna put this plus minus, I may pick them up at 37, but I definitely will see a glutamation at my AHG phase. Okay? So immediate spin, 37, an anti-human globulin or the AHG phase. Okay? Colds, don't need to manipulate, don't need to do anything. I should see a glutamation given sensitized cells in the immediate spin phase. Okay? IgG small, cannot span that gap between already sensitized red blood cells. Won't see anything at 37, so I have to do some manipulation here. I have to take this test tube and manipulate it a little bit. That will allow me to carry this test tube into the 37 phase. If I see nothing at 37, then you must follow through with the AHG. Okay? So let's look at the definition of these three phases. Table 68, page 68, table 3-8. Immediate spin. IgM class commonly detected. IgMs. Purpose and mechanism of the reaction. IgMs react best at cold temperatures, which by our definition is anything below body temperature. And this is important. Tests that we provide or recognize, or antibodies that we see and recognize using immediate spins are your ABO antibodies. Okay? That's on the reverse side. You'll get that in a second, probably next week. Reverse side means that I'm taking reagent cells. I'm just going to give you an introduction. I'm taking reagent cells, group O cells, group A1 cells, group B cells, reagent cells, okay, and mixing that with my patient's plasma. Where are antibodies? Antibodies are always in plasma, always in liquid. Antigens are always on cells. Reds, whites, platelets, I don't care. Antigens are always on cells. Your ABO type, you're either A antigen, B antigen, or the antigens on my cells. So I'm taking reagent cells as representing patient cells, okay? And I'm mixing them with my patient's plasma. I'm wanting to discover antibodies on the reverse side. I'm wanting to discover anti-A, anti-B, okay? And a few others that we'll talk about, anti-H, a few others that we'll talk about. But on the reverse side of doing an ABO type, there's a forward side and reverse side, and do both. On the reverse side, we're taking again reagent cells and mixing them with patient plasma. Okay? Expected ABO allo antibodies. Okay? Further, immediate spin phase. IgM is a glutaminating antibody that has the ability to easily bridge the distance between your red blood cells. Why? Because again, it's pendulum. It's big. Tests that we also implement the immediate spin, cross matches. Okay? Cross matches, I'll talk about that later, of course. And then unexpected cold reacting allo or auto antibodies. If we get reactivity of the immediate spin, okay, could be a cold allo, could be a cold auto, cold autoimmune hemoglobinemias, could be a cold auto. Okay, so we can discover all of that just by doing the immediate spin, but it goes to an IgM type antibody. Okay, what will the 37 incubation do for us? Okay. If we see nothing, no agglutination, no hemolysis at 37, or at cold, then we carry that same test tube over to 37. What do we may pick up in IgG? Maybe. Let me say this. Many of your Rh antibodies will begin to demonstrate some sort of agglutination, strength will vary, at 37 degrees, like an anti-PC or an anti-LC or an anti-E. Some of the RHs, Rh antibodies, will begin to demonstrate themselves at 37 degrees. Okay. Still, you have to carry that over to Hg. All right? So looking at this, IgG, okay, IgG antibodies react best at warmer temperatures, 37. When do we do these? Anytime we're searching for a clinically significant antibody, it's called an antibody screen. And then when we specifically want to identify the reacting antibody, we do an antibody identification process. What other tests do we practice and use the 37 incubation phase? Autologous controls. As in the name, autologous self. Auto control for short, autologous control. The only thing we're mixing in that test tube are patient cells and patient plasma. Auto control. No reagents, it's just patient cell and patient plasma mixed together in a single test tube. Okay? We'll run autologous controls. Two. And then 2, antibody screening and identification, which I mentioned. IgG 37 incubation. You may need to bring your cross matches into the 37-degree phase. Yes, we do immediate spins, but we can also take that cross match test tube with immediate spin and carry it to 37 and to Hg. So cross matches as necessary. And the last comment under the 37 incubation phase, IgG is sensitizing the antibody with fewer antigen binding sites than IgM, which I kind of talked about already, cannot undergo the second stage of agglutination, meaning lattice formation. Okay, so if we have sensitized IgG cells, okay, at 37, again, even though we're functioning at 37, even though you carried the immediate spin test tube over to 37, if it's an IgG sensitized red blood cell, we still will not see, okay? That's why this can be negative as well. We still may not see hemolysis and or agglutination. Again, IgG antibodies aren't large enough to span the difference and pull red blood cells together. Okay? Now, last statement under 37 incubation. Complement may be found during this reactivity 37, okay? Complement, which may or may not result in visual hemolysis. Remember I said, anytime you see hemolysis as an indicator of an antigen-antibody reaction, complement has been brought into the picture, okay? So, again, handle your test tubes, at least initially, with a great deal of care. Look for hemolysis first, then agglutination. So in 37, we may pick up hemolysis if complement's been brought into the antigen binding with the antibody. All right? Lastly, the Hg phase. It's extremely important. Okay? Antiglobulin test. Or we're using a reagent called AHG, anti-hemoglobin. This particularly is set up so that we can recognize clinically significant IgG antibodies. Okay, so we're carrying over the test tube in the skin, 37HG. Referred to as an anti-globulin test, or an AGT. Look at this, we're going to use anti-hemoglobulin as a reagent, reagent. It has a specificity, and this is always a good board's question, has the specificity for the FC portion of your monomeric unit. Has he mentioned that yet? The FC portion, has he mentioned that yet? I have last week, but I didn't emphasize it. Okay. So, AHG has propensity to look for and bind to the FC portion of the heavy chain of human IgG molecules. Or, if we use an anti-complement AHG reagent, it will bind and it will recognize complement and bind to complement. When do we use AHGs? Antibody screening and identification. Why? We're looking for unexpected warm, clinically significant reacting allo and auto antibodies. Okay. What tests? Yes, antibody screening, antibody identification, cross-matching, autologous controls, and something called ADAT, which I'm going to talk about probably next week. Okay. So 3 phases for all of those tests. Okay, not the ABO grouping, but for all of the other tests. Antibody screening, antibody identification, cross-matching, antigen typing, which I haven't mentioned. We often carry all of our test tubes through these phases. Now, lastly, and this is what I want you to review, potentiators. By the way, take one of these. Okay, potentiators, several, and we're going to use all of them. AHG, you know that goes to the anticoagulant test, the AHG phase. Okay. What does this reagent do? There's all kinds of AHG reagents out there, and I'll show you those when we get to the lab. Their purpose, AHG's purpose is to cross-link sensitized cells. That allowing visual illumination. I'm just going to run through these for them one time. We will use 22% bovine albumin. Okay? Bovine means cattle. Cows. Okay. What does it do if we use bovine albumin as a potentiator? Causes agglutination, but by adjusting the zeta potential between the cells, and that goes to the sodium cations and the thickness of the sodium cation cloud. So it adjusts that potential, minimizes that potential, so red cells become bigger, a little bit quicker. Okay. LISS, this is the one we're going to use primarily. Low ionic strength solution, or LISS. Low ionic strength solution, what does it do? It causes red blood cells to take up the antibody more rapidly. So, shorter incubation. Albumin is a 60-minute incubation. If we use that in our 37-degree phase. So this is where we add a selection of potentiators. Here, we add various potentiators to our 37-degree phase. And it could be any one of these, depending on what we're shooting for. If we add albumin, it has a 60-minute incubation. if we add LISS, minimally 15, so we save ourselves a little bit of time. Minimally a 15-minute incubation. What does LIS do as a low ionic strength solution? Again, it allows the red cells to take up the antibody much quicker. How? That's what your homework is. How does LISS work? How does LISS allow for the red cells to take up the antibody quicker? PEG. It's polyethylene glycol. In essence, it's antifreeze. It's the same stuff you put in your car, but we use a different concentration. And it's a little cleaner, it's a little more sterile. Okay. PEG, polyethylene glycol. What does it do? It increases test sensitivity. Okay. Aggregates red blood cells, causing closer proximity of the red blood cells to one another, allowing for antibody cross-linking. I want you to look into that a little bit more than what's given here. And I did give you a little more information on the unit that I provided. We use PEG selectively as a potentiator. Now, enzymes, we use enzymes selectively as a potentiator, okay? What do enzymes do? Reduce the red blood cell surface charge, which is dictated by what chemical, and I told you this already. What allows for the negativity of your red blood cells? What's in the membrane? What chemical in the membrane allows for red cells to be negative? You forgot already.
Chloride? Is it chloride?
Nope. Chloride's around, but not in. Cyanic acid. Okay. Carboxylation of cyanic acid, which is called NANA, by the way, N-A-N-A, stands for N-acetyl-nuramic acid. N-A-N-A. Okay. There's one step and a two-step procedure. We're going to do both. Now there's 4 enzymes. Number 1, physin. Number 2, papain. Number 3, bromelates. And number 4, trypsin. So there's 4 enzymes that we can use. Physin, which we will use most often, by the way. Papain. Bromelates. And trypsin. I'm not sure if I gave you the 4 in the unit that I provided or not. If need be, I'll mention those again. Okay. And then lastly, sometimes we use, which is not on this, is lectins, which is the sheet I gave you. Okay. There are several lectins that we can use. Now, what are lectins? This really isn't a potentiator, but it's a common reagent that we use in blood banking. Okay? They're antibody-like material that are extracted from plants. A lectin is a plant extract that behaves like an antibody. It's not an antibody, but it behaves like an antibody. And if you look at the listing, okay, the lectin that has A1, group A1 specificity is Dolces biflorus. Okay, we're going to use that. Then there's H, which is Ulix europaeus. Then there's Ibris amari, which is M. You can see the rest of the list here. So lectins are plant extract material that behaves like an antibody, not an antibody. It's not an IgM or an IgG or an immunoglobulin. It's just a chemical in plants that behave very, very, very much like an antibody. And we can use that depending on various cases and things we're looking